All right, so let's check out the practice homework 5.1. And the first one into practice is this chandelier. And we're going to do our free body diagram on that point where everything meets. We'll have the chandelier has mass, always going to have weight down, acting upon it. We have a cable, which gives us tension going up this way. They're calling that cable 2, so I'll call that tension 2. And we also have another cable going off, tension 1. And they give us some angles here. And the angles they're giving us, if I extend that out, this one and this one. And using some geometry, form our kind of rectangle there. This angle will be this angle. And drawing our rectangle here, this angle will also be this angle. So let me just draw a clearer picture there. Our free body diagram is the weight down, tension 2 going off this way at our angle theta 2. And then our tension going off this way at our angle theta 1. And then we will sum the forces in the x direction. So we're looking for just the components along our x-axis. And we have this T1, this component right here going to the left. That's the adjacent side for this right triangle. And what gets us adjacent is cosine. So this component here, pointing in the minus direction, and that component is T2 cosine of, oh, I'm sorry, that's T1 theta 1. And in the positive direction, this component of this right triangle, again, the adjacent, going in the positive direction now. So we would get a positive T2 cosine theta 2 there. And Newton's second law says that equals ma, but the chandelier has no acceleration, so this ultimately equals 0. And if we sum the forces in the y direction, we have this component going up, this component going up, and then weight coming down. So now these components going up are the opposite leg of that right triangle. What's going to get us the opposite here then is sine. So looking at T1, this component going up, positive direction, T1 sine. This component going up in the positive direction, T2 sine. And then minus our weight. Newton's second law says that equals ma, but the chandelier is not moving, so acceleration is 0. The whole equation then equals 0. And so we have these two results. We have from the x direction, we got minus T1 cosine theta 1 plus T2 cosine theta 2 equals 0. And from the y direction, we got T1 sine theta 1 plus T2 minus mg equals 0. And ultimately the problem wants us to find tension 1. So we're looking for T1 here, which means we need to get rid of T2. So we're going to have to do some substitution. And first one would be easiest to substitute just because it has less terms there. So I'm just going to solve this for T2. So I'd get T2 cosine theta 2, move the other stuff to the right, which makes it T1 cosine theta 1. So I'm looking at this one, this first one. And then divide by cosine. And take this result for T2 and stick it into the second one here, right there. So we would get T1. Now instead of T2, we've got T1. And now back, so it's times sine theta 2. And that minus mg, we're just going to move it to the right side to make that a plus mg over there. And sine divided by cosine here, theta 2 is tangent. And we're solving for T1. So we've got T1. Whoops. That's supposed to be a cosine theta 1 tangent theta 2 equals mg. That's a terrible cosine there. To solve for T1, we got to factor it out. And then, to finally solve for T1, we'll just divide by the parentheses. And without any numbers, that is our answer for T1. And I admit, I'm going to go kind of the lazy route here. And, well, that's what I would type in. And I'm just going to request the answer. All right, well, that is unexpected, the result they have. And I just had to do a quick check of that. So I did just some little scratch work off camera there. But I ended up turning sine and cosine into tangent. Nothing wrong with that. That's how I got my final answer there. They chose a different route. They ended up multiplying everything by cosine, which is how it becomes an numerator. And then we get this result in the denominator, which can be simplified to this expression using a trigonometric identity. And that's what's unexpected here. I didn't think they'd use using an identity. So on the test, I will absolutely accept something like this, as that is a right answer. And I'll admit, this other one looks nicer, a little bit more compact, but this is still also equally a correct answer. So check out the next one, but the thing I just want to state there again, I wouldn't do that to you on your test. Trigonometric identities is a valuable thing in simplifying, but we're trying to really focus on getting to physics. So let's check out the next one. So we got our car. Here's the car. It's that dot. And then there's tension going up the ramp. We got its weight coming straight down. And whenever you have contact with a surface, there's a normal force, always perpendicular with the surface, our surface being on an angle like this. And they do tell us the weight, 1.76. And they want to know what ramp angle would be needed in order for the cable tension to equal 1/2 of the car's weight. So here's where an angled coordinate system would be valuable, because two of our forces are in a 90-degree direction here. Nice with a coordinate system if we put it on an angle there, and call that x, call that positive y. And then here's our angle. The angle of the ramp goes there. And then we would sum our forces. And just say here's something I mentioned in class with the angle. Something that's helped me is if you think about the ramp going flat, which means the normal force is going to start to go straight up and down. And then you look at which of these angles ends up closing when you do that. So if I take this axis right here and I straighten it out, you can see this angle alpha is what goes to 0 as I straighten my ramp out. And if I tilt my ramp, here's the angle that the ramp has. So summing our forces in the x direction, we got our tension, positive x. None of the normal force is in the x direction, but some of the weight is. This component here going into minus direction. The opposite angle of this right triangle, the trig function that'll get us the opposite here, is sine. So we're going to have our weight sine of that angle. And those are our x forces. This one's in the positive direction, this component in the negative. Newton says it equals ma, but we're not moving. Or are we? Didn't read that part. Oh, so this is the setup for what they work out here. So it is important to know they don't say anywhere that the car is at rest or with constant velocity. Oh, it does say right here. All right. In this example, we will see how to handle the case of an object resting. So it is resting. There's our key word to tell us what the acceleration is. So Newton says this equals ma, but they're telling us it's resting, which means the acceleration is 0, and so the whole equation equals 0. Looking at the y direction, we got going up the normal force, all in a positive y. And in the negative, we've got this component here going in the negative direction. That's the adjacent angle of the triangle. Cosine will get us adjacent. And Newton says it equals ma. But the car is not going up or down on the ramp in the y direction here. So the acceleration is again 0, which makes the whole equation 0. And the first equation tells us tension. So just looking at this one, moving this term to the right side, tension equals weight sine alpha. The second equation, moving this to the right side, tells us the normal force equals mg cosine alpha. So let me look again at what the question is. So we want the ramp angle that's needed for the cable tension to equal 1/2 of the car's weight. So I'm taking the last part of the question here, turning it into math. Tension to equal 1/2 the car's weight. So there's our math equation from those words. And let's plug that in here. So we would have 1/2 weight equals weight sine alpha. Weights will cancel. And we get 1/2 is sine alpha. And if you remember some stuff from trig, this is one of those special angles that we encourage you to remember. And that angle is 30 degrees. And there's our answer. If we did have a more complicated angle, we would use inverse sine. So if we had something more complicated, we would apply inverse sine to both sides. Inverse sine of sine gives us alpha then, and then this is what you'd plug into your calculator. Make sure it is in degrees if you would do that. Check out the next one. So, an adventurous archaeologist, or perhaps Indiana Jones, and we got this setup, and these angles are the same, and then we've got our weight hanging here, the person. And here's, in a sense, our free body diagram. You know, tension going this way, tension going this way. These angles being the same means this is exactly in the middle. So these tensions would have to be the same. Put down a coordinate system. And get these angles into the right spot on our coordinate system. So here's my rectangle. Means this angle here goes here. And this angle goes here. So just to write a cleaner picture there, we've got weight going down. Tension going here at our angle, and another tension here going at that angle. And we'll sum the forces in the x direction. So on the left, we're looking at this component of the right triangle there. That component is the adjacent angle, adjacent side. What's going to get us adjacent here is cosine in a negative direction. So we have negative t cosine that angle. Also in the x direction is this component of this right triangle. In the positive direction, it's also the adjacent leg. In the positive direction, adjacent there is going to get us cosine. Newton says this equals ma, but we're just hanging there. So our acceleration is 0. Looking at the forces in the y, we got these components going up. And they're both the same. So this is the opposite leg of the right triangle. What's going to get us opposite sine? Both these are the same, so we'll have two of them. We'll have two of this T sign. And then in the y direction, we got weight going down. And he's just hanging there. Newton says it equals ma, but a is 0 because he's just hanging there. So that equals 0. And we do have our hero's mass, 70 kilograms. So weight is mg. They're telling us the mass here is 70 kilograms. And the first question is also asking about tension, which our second equation is going to help us with, because the first equation is just telling us these two balance out. They equal each other. T is just going to divide out there in the first one. Not much we can do. But the second one is where we can do some stuff. I'm going to move the weight to the right side. Weight, remember, is mg. And we're solving for tension. So tension will equal mg and divide by the 2 sign. They're telling us the mass is 70, g is 9.8, and they're also telling us the angle is 10 degrees. And I will punch that in real fast. So 1975. And 1980, so they're using significant figures there, but they would have taken also 1975. Let's look at part B. What is the smallest value the angle can have if the rope is not to break? So in this part, they do tell us the rope will break if the tension exceeds. So the tension that it breaks at, 3. And we got times 10 to the 4th. So we're going to have 5, 0, and then 2 more zeros there. So that's the tension it'll break at, 35,000 newtons. And so now they want us to solve for the angle, with tension now being this breaking value. So they're saying if tension is right at this breaking value of 35,000 newtons, then what must the angle be? That's right at that breaking point. So now we're solving for the angle. So a little cross multiplying, bring the sign over here, get to 35,000 down here. And then finally, to get our angle, we'll use the inverse sine. So inverse sine of sine gets us theta. And then inverse sine over here of our mg. And then 2 times 35 is going to be 70,000 there. And I'll punch that in. And that is a pretty small angle, 0.56 degrees. And what do they got? 0.56. And they did carry the 2 there, 3 sig figs. Yep, the next digit would be a 2. All right, let me try this again. Little technical difficulties. Here's this problem again. Similar to one we did in class, although a little different. One of the things unfortunate about this picture is this dotted line is drawn at an angle, but they don't give us the angle it's at. And that's all very unfortunate because we're going to assume this dotted line is horizontal. And they should have just drawn it that way. So for the foot, we got our tension going up. Another tension pulling down on the foot. And we've got these angles. We're going to take this as horizontal. 35. And that's for the foot. The weight is just coming straight down. Tension 2 is holding that up. To make these two work out nicely is why we need a horizontal coordinate system there. And from the weight, no x forces, no forces in the x direction, but in the y, we got T2 up minus weight down. Newton says is equals ma, but the weight's not moving, so a is 0, and we get that tension 2 equals the weight. On the foot, if we sum the forces in the x direction, we have two components pointing to the right, one from T1 and one from T2. Both the adjacent leg, what gets us adjacent is going to be cosine. So we got T1 cosine pointing to the right, and we also have T2 cosine pointing to the right. And then what the problem says is that this force directed along the leg must be 30 newtons. So they're telling us this force directed along the leg, that's got to equal 30 newtons. And then in the y direction, we got this component going up, the opposite. What's going to get us opposite there is sine. T2 going down in a negative direction. Also the opposite leg. Use sine. Foot's not moving up or down. Acceleration is 0. So the whole equation equals 0. So we need to find our weight. So we're going to take this T2 equals weight, plug that into these T2s to get rid of them. So instead of T2, we got weight. And we can substitute T1 here, plug it into another one. I'm going to choose the bottom one to solve for T1 because it's a little bit easier. So move the W sine 35 to the right side and then divide by sine 35. And we actually get that T1 equals weight. And so we can plug that into the other one. So we would have weight cosine 35 plus weight cosine 35 equals 30. So we got like terms. 2 W cosine 35 equals 30. And then finally, to solve for weight, we have 30 divided by 2 cosine 35. And I will plug that in. So the weight, 18.3 newtons. And to two significant figures, that is 18. Let's check out the next one. So we got a ramp, some blocks, and what are they calling these? A and B? Let's look at A first. So here's the block. It's that dot. And it has a tension 1 pulling it up. It's got a tension 2 pulling it down. That's what's connecting to block 2. Block A has a weight going straight down, and then a normal force perpendicular to the surface. Easiest here to choose a angled coordinate system because we have 3 vectors then in the direction of this angled coordinate system. And then the angle for the ramp, which they're calling alpha, that angle goes right here. And we sum our forces in the x and y direction. So x, we got this T1, all positive and in the x direction. Normal force, all in the y. T2 in a negative x direction. And this weight component is also in the negative x direction. That component is the opposite leg. What's going to get us opposite there is sine. And it does say the blocks are held in place, so they're not moving, which means the acceleration is 0. Looking at the y direction, so T1 and T2 have nothing in the y direction. Normal force completely in the y direction, positive. And then this component from weight is in the x direction, negative. It's the adjacent leg of the right triangle. Cosine will get us the adjacent. Not moving up or down on a ramp, just sitting there. So the acceleration is 0, which means the whole equation equals 0. For block B, here's our block. It's got tension 2 holding it up. It's also got its own mass going down. And then a normal force perpendicular with the surface. And I really should subscript all these with B to differentiate it from this, which is all from A. Using angled coordinate system here, since we've got 2 vectors nicely in those directions if we choose an angled system. And then that means the ramp angle goes there. Sum the forces in the x. We have tension 2, all in a positive x. This component here in the minus x direction, the opposite leg of that right triangle, what's going to get us opposite is sine. It's not moving left or right. Newton says this equals ma, but a is 0. And then the y direction. What's in the y is the normal force for B. We have this component from weight in a negative direction. That's the adjacent leg. What's going to get us adjacent there is cosine. It's not moving up or down. acceleration is 0. So they want us to find TAB. So they're calling TAB this tension right here, which is what I'm calling tension 2. It's connecting these two here. That's what they're looking for. I'm calling that tension 2. And we have these 4 equations. And I'm going to need another piece of paper. So we got these 4 equations. And we need to figure out, how can we write tension 2 in terms of just the weight and the angle? I do need to check something. They say these are 2 blocks with the same weight. So they have the same mass. They do have the same mass. So that means all of these M's are actually going to be the same, since the block have the same mass. And let's just see what happens. So we know there's a tension 2 here. So why don't we try to isolate that one? So I'll just move this tension 2 to the right. And we would get tension 2 is tension 1 minus mg sine of our angle, or mg is weight. Oops, there we go. So that's this first equation right here, rewriting it down here. Now the second equation doesn't have any tension in it, so, how's that going to help us? We need to find tension, and there's nothing in this equation that's got tension, so it's not going to help us here. If we go to this block B, again, the y direction has no tension in it, so not going to be helpful to us. But the x direction does have tension, and from that we see tension 2 is mg sine of the angle, where mg is weight, and we get sine of the angle, and that is in the form they want. They want this tension to be only of weight and the angle, and so we just satisfied that. So W sine alpha and there we go. They have a lowercase w there. Let's check out part B. In terms of the weight and the angle, calculate the tension that connects block A. So that's what I called T1. So now they're asking for this tension connecting to the wall. I called that T1. We go back to our equations that have tension. It's just these two. Now they want tension 1, which is only in this equation. So we have no choice but to use that. So I'll solve this for T1. So I'll just move the mg to the left side. And we would get from that T1 equals T2 plus mg sine alpha. And we know T2 is W sine alpha. So that means tension 1 is W sine alpha plus mg is weight. And then we have another sine alpha. These are like terms, so we got 2 of them. So tension 1 is 2. W sine alpha is the tension holding it all up. And then there is our 2W sine alpha. Check out part C. Calculate the magnitude of the force that the incline exerts on each block. So that's the normal force. So now if we go back to the first paper of work, we see we have our normal force is the y direction. Now both of these are the same because the mass is the same, so I don't need to differentiate. There's 2 masses here. They're both the same mass. So both these y equations are actually the same. And we get, solving for that, mg cosine 35, where mg is weight. So we get W cosine 35 is what they're looking for. And give it a second. There it is. Had to go through its little program in there. Part D. Interpret your answer for the case when the angle is 0. So our main work are the sum of forces. So these 4 equations, that's our main work here that we keep deriving our answers from. So I'm going to go back, I keep going back to these. So now they're asking, what if this angle was 0? As I say really fast, I'm just noticing this. I used 35 here. That's actually from the previous problem. That's alpha. I'm just catching that now. I wrote 35 there. That was actually the value from that previous problem with the leg. I meant that to be alpha there. And I did use alpha in the other ones. So now here's alpha in these. Not quite sure why my brain broke there. But that is alpha. I even said alpha when I mentioned that. So that is alpha. And now they're telling us what happens if we make alpha 0. So if we look at these 4 equations again, say this top one. So we'd have, if I can get that on there, T1 minus T2. But alpha going to 0, sine of 0 is 0. And so all that equals 0. And so we would get T1 minus T2. In other words, the tensions would have to be the same. And if we just look, we can see that the first 3 selections, these first 3, all have the tensions equaling. The last one doesn't, so the last one's wrong. But the first 3 have the tension equaling. Now they're asking about the normal force. So let's look at the normal force result. We have N. Let me just rewrite that because I have the 35 there. Cosine alpha equals 0. And they're saying, well, what if alpha goes to 0? Well, cosine 0 is 1. And so we would get N minus mg equals 0, which means the normal force is the weight. And the net selection is only this first one. So we have the tensions equaling, and they actually do all equal 0. I didn't state that anywhere. I'm just recognizing that would come from this equation here. So just looking at this one, it says T2 minus weight sine alpha equals 0. As alpha goes to 0, sine 0 is 0. And so we would get tension 2 is 0. And then coupled with tension 1 has to equal tension 2, and tension 2 equals 0, means all those tensions will equal 0. And we have our normal force equals the weight. And only the first selection of these 4 give us that. Only the first one does. And the last part, what if we made it 90 degrees? So now the ramp is just straight up. So now the blocks are hanging. Now the blocks are hanging. So making the angle 0 means they're just laying flat in the ground. No tension is needed anymore in the ropes. It's just laying flat in the ground. Making the angle 90 degrees means it's now hanging vertically. And we can make conclusions off of that. of what the answer can be here, but let's just go back to the math again and see what happens. So this first equation, if alpha goes to 90 degrees, well, sine of 90 is 1. And so we would get our tension 1 minus tension 2, and then minus mg. Because sine of 90 is 1. If we look at the normal force, if alpha is 90, cosine 90 is 0, which means the normal force would equal 0. So from that second equation, we would get the normal force equals 0. If we go to our third one here, if alpha is 90 degrees, sine of 90 is 1. And so we would get T2 minus mg equals 0. And for the last equation, if alpha is 90, cosine 90 is 0, the normal force would have to be 0, which is something we've already got written down. So this one tells us tension 2 would have to equal the weight of one block. After all, that tension holding up block B is only holding up block B. So only that weight. Well, if we look at tension 1, move all this stuff to the right side, tension 1 is tension 2 plus mg. And since tension 2 is also mg, we get T1 equals mg plus mg. So T1 is 2 times the weight. So let's see. So we also have, because I see that other stuff there, we also have T2 is just equal to the weight. So we have T1 twice the weight, T2 the weight, normal force is 0. This is what we're going to be looking for. So our first one says the tension's equal. That's wrong. The next one says tension AB, which is what I'm calling tension 2. Tension 2 equals weight. That's what they say. Tension 1, the one connecting the wall, is twice the weight. That's what they also say. And they say the normal force is 0. So the second one is the correct one. Just looking at the others, the other two here say the tension's equal, which is not the result we got. So the only one here that's possible to be true is the second one. And that is 2 blocks on a ramp. And the last one is a speaker, I guess, just hanging there. All right, well, here's the speaker. It's that dot. There is a tension 1 going that way. And I'll call this other one tension 2 going that way. The speaker has mass. That creates a weight going down. Looking at the picture, the angle they give is right here. Since these angles are the same, and both of these triangles, so the triangle made in the picture here in Mastering Physics, both these triangles are the same. So that means actually these tensions will also be the same. So let me just call that tension altogether. No need for a subscript there because these right triangles are exactly the same. So that means their hypotenuse, all their legs, everything are going to be the same. So these hypotenuse, these hypotenuses here have to be the same, which means it's the same tension. And looking at our sum of forces. in the x direction. We got tension pulling off into the positive x direction. The adjacent angle, what gets us adjacent here, going to be cosine of whatever that angle is. To the left, we have the negative component. Same tension, same angle, but going in the minus direction. Newton says it equals ma, but a is 0 since it's not moving. And we get a trivial statement from that the two tensions are the same, must be at the same angle. Nothing valuable there. Let's look at the y direction. Going up, the opposite leg. What's going to get us opposite is sine. This is also going up, that component, the opposite leg. Another sine. And we have the weight all in the negative direction. It's not moving. Acceleration is 0, so the whole thing equals 0. These are like terms, so we can add them together. Move the mg to the right side, since we're ultimately solving for tension here is what the question wants. And so tension is mg divided by 2 sine theta. And they do want a number here. So we know the mass. They're telling us it's 15 kilograms, so standard units there. So we got the mass, G 9.8. What we don't have is the angle, but they do give us the dimensions of these right triangles. So they're telling us that the height is 1.8. Yep, that's 1.8. And they're telling us the hypotenuse length is 3.5. Oops, there's my picture there. So we have these two legs, hypotenuse and the opposite. And what relates the angle, opposite, and hypotenuse is going to be sine. Sine is the opposite over hypotenuse. So using an inverse sine, 1.8 over 3.5, I will punch it into my calculator. So 30.9 degrees. That's our angle. I'm going to take that and put it into here now to get my actual numeric answer for the tension. So I'm going to plug that in. So 143 newtons. And 143. And that is the only part to that question. So all good stuff. My two, complaints here would be this leg, dotted line, should have been drawn horizontal. Very unfortunate. It is drawn at an angle. And the other one was this first one. Very unexpected that they were going to use a trig identity. Didn't expect that. That might cause some confusion too if you look at that answer, wondering how the heck did they get that. They used a trig identity. But I just want to be absolutely clear. Not using it still gives you the correct answer. It's just a matter of kind of a subjective opinion there and what looks nicer. I do think this looks nicer and more compact, but the other answer is still equally right. So there's the homework. See you Tuesday.